In the last class, I was solving a problem or I was designing a isolated footing which was resting on clay, and I did the bearing capacity analysis now, and it was safe against the bearing. Now, today I will check whether that foundation dimension that I have chosen, it is safe against settlement or not. So, as I mentioned, this was the shallow foundation, and we are designing a single isolated footing, and the problem that was taken. So, I am just quickly drawing that problem again. So, this is the ground surface, and this was the foundation. So, depth of foundation was chosen as 2 meter. So, this is ground level plus 0 meter, this is minus 2 meter. Water table location was also at 2 meter, and there was 3 layer. So, this is layer 1, 2 and 3 layers. This is layer 1, this is layer 2 and this is layer 3, and that layer 1 it is silty clay with unit weight was 18 kilonewton per meter cube. Cu value was 30 kilonewton meter square, and E value was 18,000 kilonewton per meter square. So, this is 18, and the second layer, and Cc 1 plus E 0 was 0.07 for the layer 1, and for the layer 2 unit weight was 19 kilonewton per meter cube, and Cu value was 20 kilonewton per meter square. E value was 12,000 kilonewton per meter square. Cc 1 plus E 0 was 0.15. Similarly, for the layer 3 unit weight was 19 kilonewton per meter cube. Cu value was 50 kilonewton per meter square. E value 30,000 kilonewton per meter square, and Cc by 1 plus E 0 was 0.12. So, this is the problem, and the assumed B value was that we assume a B value, that is 3 cross, and the L value is 3. So, 3 meter. So, it is a 3 meter cross 3 meter foundation or footing, and depth of foundation was 2 meter. So, this was the chosen problem. So, our this width of footing was 3 meter. Now, the total load that was coming Q was 600 kilonewton, and as I mentioned this Q is the total load including the self weight of the foundation. So, if the only weight is given, so you can add 10% of that load as the weight of the foundation. So, here this 600 kilonewton is the load including the foundation load. So, now when we are checking the bearing capacity, we use the Skempton bearing capacity expression, and the Q net safe was coming out to be or Q net ultimate was 181.33 kilonewton per meter square, and the Q net load or stress that is acting on the base of the footing is 600 divided by 3 cross 3, that is 66.7 kilonewton per meter square, and the factor of safety was 181.33 divided by 66.7, it was 2.7 greater than 2.5. So, it is safe. The dimension that is chosen, it is safe against bearing. Now, we have to check whether that dimension is safe against settlement or not, and so it is a 3 meter width. So, the influence zone for the settlement will be twice of B. So, it will be 6 meter. So, and the this second layer dimension is minus 0.4 meter, minus 4 meter, then the this layer is 6 meter, minus 6 meter, this is minus 10 meter. So, the thickness of this portion is 2 meter, then the second layer thickness is also 2 meter, and the third layer thickness is 4 meter. So, the influence zone is 6 meter, but total thickness is 4 plus 2 plus 2. So, 8 meter. So, here also the half of the third layer will be in the influence zone for the footing, because it is twice B and twice B is 6 meter. So, this is 2 meter, then another 2 meter, then another 2 meter. So, 6 meter up to this is the influence zone. Okay. So, we have to take first immediate. So, for the consolidation settlement calculation, you are taking 3 points. So, this is B and this is C, A, B, C. So, A is this is 2 meter. So, it will be 1 meter from the base of the footing, because it is half of in the middle of the layer. So, B is also 1 meter from this layer, and C is also 1 meter from here. Okay. So, these are the all dimensions. Now, what so I will do the immediate settlement calculation, then I will do the consolidation settlement calculation, and then we will check whether the total settlement is coming out to be within the permissible limit or not. So, next one is the settlement calculation. So, first one is the immediate settlement. Okay. So, the immediate settlement is Q n B by E 1 minus mu square into I f. Okay. So, the Qn value is given 66.7 kilonewton per meter square and B is equal to 3 meter, and for the clay mu value is taken as 0.5. As I mentioned, for the clay we will take the mu value as 0.5 and for the sand we are taking 0.25 to 3. Okay. So, last problem I took 0.3. So, the IF value, so it is a square footing and we are taking the center. So, the IF value will be, so from here you can see for the square footing at the center IF value is 1.12. Okay. So, the IF value we are taking from the table is 1.12. So, this table was given. So, you can use that table. So, the same table I am using, this is for the different shape and for the rectangular footing also. So, this is the table for different center, this is corner, average, and this is for the rigid foundation. As I mentioned, we are taking the IF value of the center of the flexible foundation, then we apply the rigidity correction as 0.8. So, here also, but it is a isolated footing. So, it is a flexible foundation. So, you are taking the center for the square footing which is 1.12. So, next one is that, so Q I value will be Q n 66.7, B is 3, 1 minus 0.5 square into 1.12, and for the E value. So, if I go back to the problem, so it is a 6 meter and E value is different for different layers. So, as I mentioned, I will take the weighted average of this E value. So, the E value that I am taking, E average will be equal to, first layer E value is 18,000 kilonewton per meter square, thickness is 2 meter plus 12,000, again thickness is 2 meter plus 30,000, again thickness is 2 meter divided by 6, and that is equal to 20,000 kilonewton per meter square. So, that 20,000 I will use here. So, the calculated value is 8.4 millimeter. Okay. So, now we have to apply in the immediate settlement, we have to apply two corrections, rigidity corrections and the depth correction, but here we will not use the rigidity correction because it is not a rigid footing, it is a flexible footing. So, we will apply only the depth correction. So, for the depth correction, so that d by root over L b, so d value is 2 meter, root over L is 3 meter, b is also 3 meter. So, this value is 0.67 and L by b is equal to 3 by 3 1. Okay. So, corresponding correction factor, so you will use the correction factor and that we will get from the Fox chart. So, Fox chart I have given you, and but still again I can show you. So, this is the this chart also I have given. So, here you can see that for the clay saturated, the value of mu is 0.4 to 0.5. So, that is why I am taking 0.5. For the sand, it is around 0.25, 1.5 to 0.25, or you can say take 0.25 to 0.3 also. I am taking 0.3. So, you can take 0.25 also, but I will take 0.25 or 0.3. So, I am taking 0.3, and this is the chart that I will use. So, this is the Fox chart. So, from here I will get the depth correction. So, the depth correction as it is mentioned, you can see that d by root L b. So, this is the d by root L b. So, that is 0.67. So, 67 will be somewhere here. So, corresponding L by d equal to 1. So, this is L by b equal to 1. This line is L by b equal to 1. This is 0.67. So, L by b equal to 1. So, it will take 0.81. So, from this chart I am taking 0.81. This is d root over L by b is 0.67. Then this is L by b 1. So, corresponding correction factor is 0.81. This is the upper portion. As I mentioned, the lower portion, it is root over L b divided by d. It is just the opposite. So, that this portion we will use for the shallow foundation, this portion we will use for the deep foundation. Later on, I will use this portion in the problem when we will solve the settlement of a deep foundation or pile foundation. So, that means correction factor is 0.81. Okay. So, now the corrected immediate settlement will be 8.4 into 0.81, that is equal to 6.8 millimeter. Okay. So, corrected immediate settlement is 6.8 millimeter. So, now I will do the next part, that is consolidation settlement. Okay. So, the consolidation settlement expression is C c 1 plus E 0 H log 10 P 0 bar or sigma 0 bar del P divided by P 0 bar. So, I have taken 3 points at the center of the each layer. So, I will calculate the stresses at point A, B and C. So, water table is above is below 2 meter from the ground level. So, this portion I will use the 18, that is the unit weight is given, and this portion I will use the submerge. So, I am taking I will take the 18 minus 10 as the unit weight. So, in this way I can calculate at point A that P 0 bar is equal to, for the first 2 meter depth, 2 into 18 plus. So, if you see that this portion is 2 meter plus 1 meter, this is 3 meter from the ground surface. So, this is 2 into 18 plus 1 into, this is 18 minus 10. So, here the unit weight of water, this is the unit weight of water is taken 10 kilonewton per meter cube. However, you can take 9.81 also, but all the problems that I am solving, I will take unit weight of water 10 kilonewton per meter cube. So, that means you can take also 9.81 kilonewton per meter cube. So, this is equal to 44 kilonewton per meter square, and del P the same procedure I will use. So, del P will be 66.7 into 3 into 3 divided by 3 plus 3, because 3 plus 1, because it is 1 meter. So, 3 plus, because this depth is 1 meter from the base of the footing. So, it will be 3 plus 1 and the other side also 3 plus 1. So, this is equal to 37.52 kilonewton per meter square. Similarly, at B, your P 0 bar is equal to 2 into 18 plus 2 into 18 minus 10 plus 1 into 19 minus 10. So, that will be equal to 61 kilonewton per meter square, and del P will be 66.7 into 3 into 3 divided by 3 plus 3, because now it is 3 meter from the base of the footing, 2 meter plus 1 meter. B point is 3 meter from the base of the footing. So, 3 plus 3 into 3 plus 3. So, that is equal to 16.7 kilonewton per meter square. Similarly, at point C, P 0 bar is equal to 2 into 18 plus 2 into 18 minus 10 plus 2 into 19 minus 10 plus 1 into 19 minus 10. So, this is equal to 79 kilonewton per meter square, and del P is equal to 66.7 into 3 into 3 divided by 3 plus 5 meter, because now it is 5 meter from the base of the footing plus 5. So, that is equal to 9.4 kilonewton per meter square. So, the settlement value is coming out to be, this is for the first layer C c divided by 1 plus E 0 is 0.07, thickness of the layer is 2 meter, and this is log 10, P 0 bar is 44, del P is 37.52 divided by 44. Then for the second layer it is 0.15, thickness of the layer is 2 meter, this is log 10, this is P 0 is 61 plus del P is 16.7 divided by 61. For the third layer, this is 0.12, thickness of the third layer portion within the influence zone is 2 meter, then log 10, it is 79 plus 9.4 divided by 79. So, the total settlement is 80.75 millimeter. So, the correction factor. So, next we will calculate the correction factor. So, total uncorrected settlement is 80.75 millimeter, and correction factor so for the depth correction factor is equal to 0.81, and pore water pressure correction factor is, because we are taking corresponding A value is given as 0.6 and H t by B, H t by B here, H t is twice B we are taking and B is here. So, it is 2. So, now if I go to the chart, then this is the chart where this is the correction factor, and here we are for the circular footing I am using, because it is a square footing, because here steep or circular is given. So, for normally consolidated soil, this is A value is 0.6, this is the H t by B of these values. So, this is H t by B equal to 1, this is H t by B equal to 4. So, it is in between that. So, 0.6. So, this is the value, correction factor is 0.7. So, the correction factor will be the 0.7, and so corrected settlement, consolidation settlement is 80.75 into 0.81 into 0.7. So, that is equal to 45.75 millimeter. So, the settlement total is equal to 6.8 plus 45.75. So, that is equal to 52.58 millimeter. So, in the permissible settlement part, I have given that for the isolated footing RCC on sand, permissible settlement is 50 millimeter, and for RCC isolated footing on clay or sensitive clay, here it is that type of clay where it is soft clay. So, or medium clay, their permissible settlement is 75 millimeter. So, our settlement is less than the permissible settlement as per the IS code. So, our design is safe. So, it is safe against bearing, it is safe against settlement also. So, the dimension that I have chosen is safe. And so, now another thing I want to say that sometimes this dimension may be over safe also. So, you have to redesign that, but here it is not over safe because your factor of safety is 2.7, which the limit is 2.5. So, it is not over safe, we can say in terms of bearing, but in terms of settlement it is 50 degrees 75. It is slightly you can increase the settlement further by reducing the dimension, but for the bearing purpose you cannot further reduce the dimension. So, the dimension that I have chosen is almost okay and safe as well as economical, because our in design criteria there is two things. We have to make these foundations such that it is safe against bearing and settlement as well as it is economical. So, here we can choose this dimension because it is safe against bearing as well as the settlement. So, this is the isolated footing part, and then I want to say a few things that. So, yes. So, as I mentioned, so these tables I have used for the purpose. So, let me check another thing that I am coming back on these tables. So, we have done the isolated footing part. Now, similar way you can design the combined footing also. Suppose we have a combined footing of this type where there is the two columns, and we can use as a combined footing, and such that we can design it such that the load is acting at the center or the centroid of that footing, and then you can take the summation of the all load that is acting on the center, and then you design it as a rectangular foundation, or if it is too steep or narrow, then you can choose as it is a strip footing also. Okay. So, regarding this correction table, these are the tables I have used. So, this is the for the IF value. So, I have taken 1.12, I have used these values, and for the flexible square footing, and then as I mentioned, we can take the Poisson ratio of the clay as 0.5 and for the sand it is 0.3, but here it is given for the fine sand it is 0.25. So, 0.25 to 3 you can choose. So, I have taken 0.3, and then this is the correction factor for the. So, now we are using the 3 correction factors. So, for the depth one is rigidity correction factor, that is always we are taking 0.8, and that is applicable only for the rigid foundation or raft foundation, and another is water pressure correction, which is applicable for the consolidation settlement. And you can see that for a normally consolidation settlement, if a value is given is 0.6. So, this for normally consolidation settlement 0.7 a reasonable value. So, that I have used even in this chart also, this is the correction factor. This correction factor range for the normally consolidated soil is also 0.7 to 1. So, that is why if nothing is given, So your A value is not available, and so you can, in that case, for normally consolidated soil, you can take pore water correction factor as 0.7, which is reasonable, okay, if A value is not available. But if A value is available, then you have to use the chart that I have used in this problem. But if A value is not available, so for normally consolidated soil, you can take pore water pressure correction as 0.7, which is a reasonable value, and all the designs here I am doing on normally consolidated soil, and which is the most of the cases you will find the soil is normally consolidated. So, that is why you can take 0.7 is reasonable value if nothing is available. And then for the, and if the A value is available, then you can use this chart that I have used for the determination of pore water pressure correction factor for, or it is a pore water pressure correction factor. And then next one is that, and third correction factor is the depth correction factor. So, you can use this chart that I have used. So, all the problems I will not show that the chart, I will just mention that I am taking from the chart. So, this is the chart that I am using. I have explained these things in previous lectures also. So, again I am explaining. So, this is the chart I am using. So, this is the upper portion of this chart is applicable for shallow foundation, and lower portion of the chart will be used for the deep foundation settlement calculation. So, this is the just 1 by, you can see d root over L b, and this is root over L b by d. Okay. So, in few books you may find this is L b root over d, which is not correct. So, this is the correct form that you have to use, because it is a non-dimensional form. Okay. So, that is why we have to use this chart. And then next one is we are talking about the, yes. So, we are talking about now the combined footing. So, now in the next class I will discuss how I will choose the dimension of a combined footing, then I will design a raft foundation resting on clay. Thank you.